My name is Sek Chai. I'm from SRI International. SRI is a nonprofit research organization. Today I'll talk about some of the work that we're doing under the DARPA Cortical Processor Phase 1 kind of ceiling. Last year I talked about using noise as a means to train some of these networks. Today I'm going to talk a little bit some about the applications and some work that we're doing in the low precision space. This work is done in collaboration with University of Guelph, Graham Taylor and his team, and also University of Montreal, Yashua Benju and his team. In the project, what we're doing is looking at not just convolutional neural nets, but recurrent nets, things that can do time series analysis. You want to look for patterns, right? Because dominantly all the sensor data that we have has a time component. We looked at both audio, video, and gesture kind of things. And what I'll do is just show one example to motivate some of the low precision work that we're doing. Basically, the idea is you start with the benchmarks that's out there, analyze it, and then come up with what things you need to do for kind of low power, low precision, and kind of handle some of the memory issues that is currently the bottleneck in a lot of the designs. Now, what we want to do in the benchmark that I'm talking about is the Charlearn data set is really looking at humans. You want to understand what are the activities. So in this data set, they have gesture information, so body, articulated pose. There's actually videos of the left and right hands, depth information as well, and also an audio component, right? So if you think about the neuromorphic systems that we want to build, it's rich in sensory kind of data. Right? We have depth information, we have stereo pair of eyes here, we have audio sensor. A lot of those kind of things needs to be combined in a way to understand. And this is how the human visual systems kind of work, right? But today, a lot of the work in, let's say, deep learning is still, convolutional nets, which is more static imagery, right? So the question is, how does this type of sensory data, rich in a lot of different multimodal kind of things, how can we use it best? I'll jump right to the kind of results. This is work out of, again, Graham Taylor and his team, what we call deep gesture. It's state-of-art, best in class right now in terms of the Charlearn database. What you see on the top right is that we have the different sets of neural nets, right, for each of the different modality. And the question then is, how do you fuse the data together? You have something that recognizes the gesture from a video perspective, some from an audio perspective, and then some from the gesture perspective. How do you fuse the data? And right now, what we think is we adopt a strategy where we kind of fuse the modality together that are similar. So left and right hand video, left and right hand stereo pairs, and then and from the picture on the left, what you see is that as you fuse like data, the performance gets down, right? The validation lower is better, so the error gets down as you fuse the light modality, right? And that's how we get some of the performance. Anyway, I can talk more about this, but I'll just leave it at that, where one of the interesting data things that I think will solve in the near future in this community is not just one modality, but more. And then the question is, okay, how do you fuse them together? Because there is a lot of work that you have to think about how can we get brain-inspired kind of approaches for fusing some of this data as well. Now I'm going to shift gear a little bit and say, okay, this type of neural nets and this type of data set, how big is it, right? We talk about memory, we talk about precision, all that stuff, and talk about power, right? Really, how big is it? So I'm going to give you a number, right? In this Charlearn data set, we have a total up from the motion detection, skeleton, video, all that sums to get about 42 gigabytes of data. And if you number crunch it to get the state-of-the-art performance there, it took 5 days running on a high-end cluster, right? So lots of watts, running 5 days at a continuous kind of mode to get the performance that we want. So a lot of time, a lot of it is memory bounded, right? And this network that we're talking about is really large, 7.8 million kind of parameters, things that you have to tune and train for. So really large networks, really a lot of memory that you need to go through. So, and we understand that memory is indeed some of the main issues that we're trying to address here. So if memory is an issue, how do we address that, right? So some of the things we're looking at is low precision. I'll give a quick summary, although this is not comprehensive. folks that have looked at stochastic kind of rounding, you don't want to round down all the time because then you bias your result from one way or the other, or you can't round up all the time. You have to kind of statistically understand how you're rounding really up or down so that you don't bias your training results. There's very recent work from NICE 2015, folks from Stanford and NVIDIA looking at network pruning. The network doesn't need to be that big. It's really engineered, but there's a lot of redundancy in there. So as you train, you can start saying, well, some of these networks, some of these connections or nodes, you don't really need, and you start pruning them away. So you kind of scale that down. And folks out of Montreal as well have looked at, can you really train some of these data, some of these networks to be binary, right? Binary rather than floating point kind of representations. And they can show that for some data sets, they actually make sense. So what I want to show is some of the other interesting things you're doing in low precision, which is to say, what if we looked at how our visual system behave with data? And let's say we look at the compression space, right? And in compression and wavelet and subband decomposition, what we do is we can actually filter them into high and low bands. And then in the high band frequency, maybe you can start to reduce some of the bits because our visual system can't see that level of precision. Then the question is, can you do similar things from a learning perspective? In other words, if you give it the filtered high and low bands and let it train from there, and perhaps what it learns to recognize object, you can start trimming there. So not just say, I'm going to blatantly give raw pixels in, but be smart about how you provide the neural nets, right? And I'll show you some results that we've done based on this kind of basic idea. So what we've done is say, well, let's take a very simple example. This is the Google Linnet 5 and Yakun's work looking at digits. We took this architecture and say, okay, maybe we split it into just high and low band. In this case, we use Laplacian and Gaussian things. And you can kind of principally understand, the high frequency content is edge-oriented. The Gaussian low-pass filter are mostly texture kind of information. We kind of train it, and we have a fusion stage at the end, right? And cut to the chase, we show that the fusion results can get better. What happens here is that you're not giving the network lots of different raw data, but you actually kind of tell it, hey, learn more about the edge on one end, learn more about the texture on one end, can you fuse the data, and you can get better performance, right? And here we show that, comparable, you can reduce it by, 2 to 4 x in terms of the precision, right? From 32-bit down to 14-bit, which is kind of equivalent. I'm running this too really quickly. Okay, MNIST data, digits, no color. We tried it actually on thumbnail images, more natural images, because that's more interesting. That's what our kind of environment is about. And what we find actually is very compatible, right? Not as good perhaps with the raw pixel, but one thing you'll notice is that the jaggedy line is training the original network through raw pixel pushing it through. It's jaggedy, so it's learning, but it's adjusting as you go, right? But with the low and half pass kind of idea, the subband kind of composition idea, the learning is kind of smoother. And what it says is that you kind of tell it exactly what it needs to learn. You're tuning it, right? You're actually guiding it where to learn, and the opportunity comes when you fuse the learning kind of concepts together down the end. So I think that's very interesting to look at. And what it means from a training perspective and a low precision perspective is that, A, you can push the learning rate a little higher, that reduce the training time. We talk about 5 days on high-end networks for the deep gesture. You can start to say, maybe I can start scaling it back by guiding where it needs to learn, perhaps through this decomposition method. And from a low precision perspective, you can start saying, I'm going to tune the memory size down, something that, from the 40-some gigabytes of data down to a very compact mode, and even to today's processor, you start thinking about, can we put them in the cache, right? So I'll end my kind of lightning speed speech here. Really, what I'm talking about is the hybrid, multimodal kind of concepts are something that we need to look into. We are starting on that, but a lot of different ideas, hoping to get some ideas from the neuroscience community as well. Fusion, I think, would be important. How do we fuse them, right? What we showed here is a very simple fusion idea where we have equal weighted weights, but it's engineered, right? I like it to be a little bit more principled. Can we actually train that last layer rather than saying, I'm going to do some sort of summation at the end, right? And then low precision, there's a lot of promise there. I think we can look at that. I do have a poster in this conference, so stop by. I'd like to talk to you guys. Thank you.